asleep on the hay.
We're going to be talking about constant speed propellers.
Okay.
You know, you've probably heard about them.
Yeah.
But we're going to be looking at some articles that really kind of go into the nuts and bolts of how they work, why they were important to aviation, and some of the really kind of surprising history behind them.
Yeah, it's a fascinating topic.
Yeah. And I think people hear constant speed propeller, and they don't really understand what that means.
Right. And it all starts with a problem.
Yeah.
You know, early aircraft, they had fixed pitch propellers.
Mm-hmm.
And you can imagine trying to fly a plane with a fixed pitch propeller. It would be like trying to drive a car that's stuck in one gear.
Yeah. You'd either be really good at taking off or really good at cruising on the highway.
Exactly. You wouldn't be good at both.
Right. You'd be terrible at one or the other.
Yeah, exactly. So they needed to come up with a solution to that. And that's where variable pitch propellers came in, which is basically a way of changing the angle of the blades.
Yeah. So it's like having a multi-speed bike instead of single speed.
Exactly. And a constant speed propeller is a type of variable pitch propeller that automatically adjusts the pitch to maintain a constant engine speed.
So it's like having an automatic transmission.
It is. It's exactly like having an automatic transmission.
Instead of having to shift gears.
Right. It does it for you.
Okay. So how does this magic work?
So inside the propeller hub, you have these little flyweights. And as the engine speeds up, centrifugal force throws those flyweights outwards. And those flyweights are connected to a pilot valve that controls the flow of oil.
So as those flyweights get thrown outwards?
More oil is pushed into the hub. And that oil acts on a piston. And that piston changes the pitch of the propeller blades.
So it's like a little dance going on in there?
It is. It's a beautifully choreographed dance of physics.
If the engine starts going too fast.
Those flyweights are going to get flung out further, more oil is going to flow in, the blades are going to adjust, and the engine is going to slow back down.
So it's a self-regulating system.
It is. It's a beautiful thing.
Yeah, so it's actually not that the propeller speed is constant.
Right. The engine speed is constant.
Gotcha. It's keeping the engine at a certain RPM.
Exactly. So think of it this way. You're trying to open a jar of peanut butter. The stickier the peanut butter, the more torque you need to open that jar.
Yeah.
A constant speed prop is like having the perfect grip on that jar. It allows the engine to use its torque in the most efficient way possible.
It's like not struggling to open a jar.
Exactly. You're always using the right tool for the job.
Right. Now, this oil pressure system
that we're talking about is common on larger aircraft. But on smaller aircraft, you're starting to see electronically controlled propellers.
Oh, so it's like trading in your flip phone for a smartphone.
Exactly. It's the same basic idea, but with more modern technology.
Yeah.
One important thing to note about these constant speed propellers, especially on single-engine planes, is that there are mechanical limits on how much that blade angle can change.
So there's a limit to how low or how high the pitch can go.
Yes, and that's a safety feature to prevent you from accidentally going into what's called a feather.
A feather, yeah.
A feather is when the blades are aligned with the airflow. To minimize drag, you would do that on a twin-engine aircraft. If you lose an engine, you would feather the propeller on the dead engine so that you could maintain control and continue flying on the remaining engine.
Okay, so that makes sense for a twin. But on a single, you want a feather.
No, because if your only engine quits, you want that propeller to keep spinning for as long as possible.
Yeah.
Now, before we get into how constant speed propellers behave during different phases of flight, let's talk a little bit about the history.
Okay.
Because this idea of adjusting propeller pitch didn't always happen automatically.
Yeah, that's a good origin story.
So way back in the early 1900s, you had pioneers like A.V. Rowe and Louis Breguet, who were experimenting with ground-adjustable propellers.
Wow, so they would have to land.
But actually, physically adjust the pitch.
That sounds inconvenient.
It was. But that's what they had to do.
Right. Got to work with what you've got.
Exactly. And then you had some even more interesting concepts like the counterweight propellers.
Counterweight propeller.
Yeah, which used centrifugal force to automatically adjust the pitch.
So the faster it spun.
The further the weights would swing out. And that would change the blade angle.
Oh, that's clever.
It was. But like many early inventions, it had its limitations.
Right. They didn't quite get it right.
They also experimented with what were called pneumatic propellers.
Pneumatic?
Yeah. They used air bladders to change the pitch.
Wait, what?
And get this. You had to pre-flight pressurize them with a bicycle pump.
Wait, you're kidding?
I'm not kidding.
A bicycle pump.
A bicycle pump.
That's hilarious.
It is kind of funny when you think about it. But these were important stepping stones that led to the more reliable hydraulic systems that we use today.
Right.
And it was Dr. Henry Selby Hillishaw and T.E. Beecham, who really cracked the code. They developed a hydraulically operated variable pitch propeller in the 1920s, and that formed the basis for the commercially successful propellers that we use today.
Gotcha.
In fact, their design won the Collier Trophy in 1933 for its contribution to aviation.
So they're the ones we have to thank for this technology.
Absolutely.
That's really cool.
So now that we've talked about how these propellers work and a little bit about the history, let's talk about how they actually behave during different phases of flight.
Okay, let's get into that.
Right.
I'm ready to see this thing in action.
Let's do it.
We're in the cockpit. We're ready for takeoff. What's the first thing we do with that propeller control?
So for takeoff, you want maximum power and thrust. So you're going to push that propeller control full forward, which is going to set those blades to a low pitch, high RPM setting.
So it's like starting a race in a low gear.
Exactly. You need that initial burst of energy to get you moving.
But then what happens is we climb and gain airspeed.
Well, as you climb and gain airspeed, you're going to gradually pull back on that prop control, which is going to increase the angle of the blades or the pitch and allow the propeller to take a bigger bite of air. With each
shifting to a higher gear.
Exactly. On your bike, you're
Yeah.
pedaling less, but each push is more powerful.
Okay. Now, what about when we reach cruising altitude? What happens then?
So when you reach cruising altitude, you're going to fine-tune that propeller control to find the sweet spot for fuel efficiency and engine wear.
So it's a balance between airspeed,
Yeah.
engine speed, and power setting.
Exactly. It's all about finding that perfect balance.
Okay. Now, we've been talking about this in the context of a non-turbocharged engine.
Right. What happens when we add turbocharging into the mix?
Because turbocharging changes things a little bit.
It does, because as you climb to higher altitudes, the air gets thinner.
Right.
And so non-turbocharged engine, you have to constantly adjust the throttle to compensate for that thinner air.
Right. To maintain power. But with a turbocharged engine, the turbocharger is doing that for you.
Exactly. It's helping to maintain that consistent power output, even at high altitudes.
So the turbocharger is like an oxygen mask for the engine?
I love that analogy. That's a great way to think about it. It's helping it to breathe at those higher altitudes.
Yeah. Okay, so let's say we have enjoyed our time at cruising altitude.
Yeah.
And it's time to start heading back down. What happens to our propeller as we descend?
Well, as you start to descend, your airspeed is going to increase, even though you've reduced power.
Right.
And so the propeller wants to spin faster.
Okay.
But that's where the constant speed governor comes in. It automatically adjusts the blade pitch to prevent the engine from overspeeding.
So it increases the pitch as the airspeed increases.
Exactly. It's anticipating those changes and making adjustments.
Right.
To keep everything in check.
So it's almost like a human pilot in there anticipating what's going to happen.
It is. It's a brilliant system.
You mentioned earlier that there are mechanical limits on how much the blade angle can change.
Right. There are stops that prevent the blades from going too far.
So what happens if we hit those stops?
So as you reduce power during the descent, the propeller will eventually reach its minimum pitch limit.
Okay.
And if you don't anticipate this and adjust the prop control, you're going to hear a sudden increase in RPM as the propeller hits that stop.
It's like forgetting to downshift in a car.
Exactly. It's not a smooth experience.
Not a smooth experience. So how do we avoid that?
So to avoid that, experienced pilots will often manually adjust the prop control during descent to keep the RPM consistent and smooth.
So it's almost like overriding the automatic system a little bit.
It is, but it's all about maintaining a smooth, and comfortable descent.
Right, for the passenger.
Exactly. You don't want them to feel like they're on a roller coaster.
Okay, so let's talk about engine failure.
Okay, so imagine you're cruising along in your twin-engine airplane, and suddenly one of those engines decides to quit. Now you've got a dead propeller. That's just windmilling in the breeze, creating a ton of drag and making it much harder to control the aircraft. So that's where feathering comes in.
So that's why it's so important in a twin-engine aircraft.
It is. It's like tucking in your arms. When you're riding a bike downhill, you want to minimize That wind resistance.
Right.
So by feathering, that dead propeller, you dramatically reduce drag.
Okay.
And allow yourself to maintain control.
Now, on a single-engine plane, you said that's the last thing you want to do.
Well, right, because if your only engine quits, you need that propeller spinning for as long as possible.
Well, what happens in a single-engine plane if you have an engine failure?
So on most single-engine planes, if you lose oil pressure, which often happens with an engine failure, the propeller will automatically move to that low pitch, high RPM setting.
Sounds like it's trying to give you...
And last chance.
It is. It's a last-ditch effort.
That's right.
To give you some semblance of control.
Yeah.
And maybe even a tiny bit of extra power in a desperate situation.
Yeah. Now, all of this amazing technology, all of these intricate systems don't mean much without a pilot who understands how to use them correctly. Absolutely. Operating a constant speed propeller isn't just about pushing and pulling a lever. It's about understanding the why behind the how.
You have to know what's going on inside that propeller hub.
Exactly. You need to know what's happening mechanically in order to make informed decisions in the cockpit.
Because if you're not careful, you could damage the engine, reduce its lifespan, or even create a dangerous situation.
Exactly. So we've covered takeoff, climb, cruise, descent, and even engine failures. And it's amazing how a constant speed prop adapts to each of these phases, optimizing performance and safety along the way.
Yeah, it's a remarkable piece of technology. It makes me wonder if the principles behind these propellers could be applied to other fields.
That's an interesting thought. You know, we've seen how variable pitch revolutionized aviation. Could we create smarter, more efficient wind farms that adjust their blade angles to capture the most energy from varying wind conditions?
Or what about fan designs in our homes and buildings? Could we create fans that automatically adjust their blade pitch to match changing airflow demands and save energy?
Absolutely. I think the key takeaway here is that the concept of variable pitch has the potential to revolutionize more than just aviation, whether
it's controlled mechanically, hydraulically, or electronically. It's all about adapting to change, optimizing performance, and achieving greater efficiency.
You know, this whole deep dive has really highlighted the ingenuity and innovation in aviation.
It has. It's been an incredible journey of problem solving and pushing the boundaries of what's possible.
From bicycle pump-powered contraptions to the sophisticated systems we have today.
And it's amazing how far we've come.
All right. Well, I think we've successfully unpacked the magic of constant speed propellers.
We have.
And we'll see you next time.
Sounds good. It really is amazing.
So have we really gone into the heart of constant speed propellers? You know, the mechanics, the history, the real-world applications. Really stands out to you as the biggest aha moment.
You know, for me, it's the sheer brilliance of that self-regulating system. You know, those flyweights.
The oil pressure, the pilot valve, all working in perfect harmony to automatically adjust the pitch. It really is a symphony of engineering.
Yeah, and it's not just about efficiency either. You know, we've seen how crucial these propellers are for safety, especially when dealing with engine failure.
Absolutely. You know, imagine you're flying a twin-engine plane over a mountain range, and suddenly one engine goes out, feathering that dead prop. Could be the difference between making a safe landing and a much less desirable outcome.
Yeah. And even in a single-engine scenario, that fail-forward design is a real lifesaver.
Yeah.
You know, it's fascinating to think about how this technology, that was born out of necessity in aviation, could have applications in so many other areas.
It really does speak to the power of innovative thinking.
Yeah.
Yeah.
We've seen how variable pitch revolutionized how we fly. Now imagine harnessing that same principle to create smarter, more efficient wind farms that adjust their blade angles and capture the most energy from it, ever-changing wind conditions.
Absolutely. Or what about applying it to the design of fans for our homes and offices?
Yeah. Can we create a constant speed ceiling fan that automatically adjusts to optimize airflow and energy consumption?
The possibilities are endless.
It really makes you wonder, what other groundbreaking innovations are just waiting to be discovered, ready to transform the way we live and interact with the world around us?
Yeah.
Well, folks, I think we've successfully unpacked the magic of constant speed propellers.
We have.
From those early days of tinkering with bicycle pumps to the sophisticated systems we have today. It's been a remarkable journey.
It really has.
And as we've seen, the deeper you delve into any subject, the more fascinating it becomes.
Absolutely.
All right, thanks for joining us. on this deep dive into the world of constant speed propellers. Until next time, keep exploring, keep learning, and keep asking those what-if questions. You never know where they might lead.
Sounds good.
Jesus, asleep on the